have Dr. Vasily Sidorov from Anoma projects to talk about Typhon, a flexible engine for ordering and concurrent serializable execution of transactions based on heterogeneous consensus. So welcome, Vasily.
Test. Hello, my name is Vasily. I'm with Helix. And today I will tell you about our project called Anoma. This will be a slightly higher level talk, slightly more conceptual, less formulous maybe. You're looking at this slide, you're probably wondering what's a Typhon and why does it hide in the Taiga? But before we go to that question, let's answer a different question that is slightly more fitting for the conference. And the question is, what's a blockchain? And there are many different ways to answer this question. My personal favorite is that blockchain is a database. And it is a very specific database at that, with very specific properties. It is append-only. It is highly distributed and highly replicated, meaning that the distributed nodes store a full replica. It is ordered and serialized. And it stores records, and we call these records transactions. And these transactions, they contain state transitions. So the database as a whole contains the global state, and these transactions contain state transitions. So we go from one state to a different state. Typically, the state is often it's exchange of resources. I send tokens to you, you send tokens to me. But it could be anything else. It could be games, it could be ENS, basically any application that stores state on the chain, stores their data on the chain, is part of this global state. Important characteristic of state transitions that we store on the blockchain is that they often affect multiple parties. And then when we have multiple parties, we have settlement. What's settlement? It's a multi-party state transition that everybody agrees on. When settlement happens, parties already know what they settle on and who they settle with. To reach the phase of settlement, they need to figure this out. They need to find the counterparty, so who they settle with, and they need to decide on the terms of their settlement, so what they are settling on. This phase that happens before settlement is referred to as the phase of counterparty discovery. Marketplaces do this. They match sellers with buyers, for example, and help them agree on the price. But even without the counterparty discovery phase, settlement phase itself is not trivial. The simplest form of settlement is manual settlement. Let's say I want to buy some coffee for Bitcoin. I can send Bitcoin using my phone, show that the transaction is confirmed to the barista. They would pour a coffee for me, and we're done. So this is manual settlement. We can call that generation 0. Generation 1, scriptable settlement, was represented by Bitcoin and Bitcoin script. And Bitcoin script was very limited, very hard to write, hard to use. But even that gave way to a lot of very interesting projects. For example, Colored Coin, which was a predecessor to tokens as we know them today, or Namecoin, which was a predecessor to ENS. Generation 2, of course, led by Ethereum, was programmable settlement. And this opened the floodgate of possibilities. We have multiple assets, fungible, non-fungible. We have DAOs, DEXs, games, lots and lots and lots of different things. And for all of these applications, settlement happens on Ethereum. But all of these applications also need counterparty discovery. So how do they do counterparty discovery now? There are several general ways to do counterparty discovery today. We can do it on the blockchain, and this is what algorithmic market makers and on-chain order books do. We can have a centralized off-chain database, such as OpenSea, 0x relayers, Flashbots are good examples of that. Or we can have app-specific sovereign chains. DYDX is a great example of that. These approaches have their problems. If we do this on blockchain, it's kind of expensive and also unnecessary. We don't really need to store the data related to counterparty discovery on chain. Centralized databases, the problem with them is, well, they are centralized. And app-specific sovereign chains, this is a great idea, and everything is great about it, except for it's really hard to do. It requires a lot of development work, a lot of time and effort, and not everybody can pull this off. But if somehow we could generalize this use case, somehow we can make it possible that we have some kind of app-specific chain on demand, that would be great. And this is something that Anoma tries to do. Anoma is a framework for programmable settlement and counterparty discovery. And in our view, this is what a third generation of blockchain should look like. Anoma is built on several key design principles, 3 of which are privacy, intent centricity, meaning that applications written on Anoma only need to define their particular state transition rules and everything else is taken care of. And something we call homogeneous architecture, heterogeneous security. We'll talk about this in the next slides. So let's start with privacy. Privacy in public ledgers. What's the state of the art there? Well, in general, there is no privacy in public ledgers, no privacy in blockchains. But contrary to popular belief, this is not an intrinsic property of a blockchain. They don't have to store everything in the open. They don't have to be transparent. Just when we started building blockchains and we wanted certain properties, namely them being highly replicated and publicly verifiable, we just didn't know how to do this without having everything in the open. But over the time, there was many attempts at achieving privacy on blockchain and very different approaches to do that. I think the first attempts to do that were Bitcoin mixers, and initial Bitcoin mixers were pretty simple. I'm pretty sure there was just a dude somewhere you can send your Bitcoin to, and he would just send it to some other address. But then if you add zero knowledge proofs to that, and we can have something like Tornado Cash on Ethereum. There were cryptographic approaches such as NuCypher, which I think now is called Threshold. They tried to use a lot of different cryptography, proxy re-encryption, homomorphic encryption, threshold encryption, bundle all this together to achieve privacy. Secret Network tried to use trusted execution environments such as Intel SGX and AMD SAV to achieve privacy. And then zero knowledge proofs entered our lives, and a big breakthrough was Zcash, which combined the latest research in zero knowledge proofs and cryptography, great engineering, and they were able to create an actual private blockchain, which was great. It was a great breakthrough, but it was also, and still is, also very limited in its capabilities. It only supports one asset type, which is Zcash. It does not have any programmability. There is no bridges to or from Zcash, but still a great breakthrough. Whoop. Sorry, slide got mixed up. Anoma is in many ways inspired by Zcash, but it does have programmability and it supports multiple assets. By using UTXO and a lot of zero knowledge proofs, we can achieve not only data privacy, but also function privacy. When we say data privacy, we mean that we don't know amounts, owners, what happens to assets. Assets are stored off-chain in the form of node, it's UTXO. And given a node, which is not stored on-chain, we can use on-chain data to validate that the node is legit and it was not yet spent. Function privacy we mean that we don't know which contracts are executed. We don't even know which contracts generally exist. We just know that there is some contract and it was executed properly using zero knowledge proof, but we don't know what contract it was. And when we say we don't know, we mean that users consent to sharing the data with whoever they choose to share it with. So they have a choice. A second design principle is intent centricity. So we mentioned that settlement is when a multi-party state transition happens that everybody agrees on. So what does this word agrees here actually mean? On Ethereum, for example, we don't sign off on a desired state change. Instead, we sign off on execution of kilobytes of EVM bytecode, hoping that it would lead to a state change that we want. But we accept whatever state change actually happens, we accept whatever results it produces, even if we are unhappy. A good example of that is slippage when we do swaps. With Anoma, we forget the imperative because we are now in the declarative land. Using intents, we express what we want, not how to get it. We do this using binding programmatic commitments to our preferences. Those are sent to a peer-to-peer intent gossip network. And then special type of agents in the network called solvers, they look at the mempool of intents and they try to find compatible intents and create transactions that fulfill these intents. And these transactions are then settled on a settlement layer. The third design principle is homogeneous architecture, heterogeneous security. This should be on my t-shirts here under the word Anoma. And this idea behind this principle is that not all monopolies are bad. Protocol monopolies are actually good. We use the same protocols, TCP/IP, HTTP, email, and we all win from that. We all win from these protocols being ubiquitous because we get interoperability, we get diversity of vendors, and so on. However, some monopolies are bad, and security domain monopolies are bad in particular because they are controlled. Whoever controls them can cut you off completely. A good example is USDC with their blacklist of users who use Tornado Cash, for example. They can extract rent and so on. And usually, architectures and security domains, they come in a bundle, but they don't have to be. So actually, they don't have to be coupled. And in fact, in Anoma, they are decoupled. Because Anoma is not a blockchain. Anoma is an architecture for multiple different but highly compatible chains. We call them fractals. So Anoma is a set of components for counterparty discovery and settlement. And you can mix and match these components. You can use different setups, including different security setups. You can use intent gossip network on top of Ethereum and settle on Ethereum instead of Anoma. And all these fractals are highly compatible. You think Cosmos to the power of 10. You can use assets from one Anoma fractal on another Anoma fractal. You can start your own fractals that are fully managed by you or by agents that you trust. And you can even create temporary fractals for a specific occasion, transact there, and then only settle the final result to the main chain. Anoma consists of many components. There are many projects in Anoma, but today I want to focus on 3 of them: Vampire, Taiga, and Typhon. So let's start with Vampire. What's Vampire? It's an intermediate representation language for arithmetic circuits. You can think about it as LLVM for zero-knowledge proofs. Higher level languages can compile to Vampire representation, and Vampire compiles to different proof systems. Here you can see a piece of code written in Vampire. This piece of code checks if 3 numbers form a Pythagorean triplet. And we can compile and run this code. We can compile this circuit into Hello2 circuit. We can then try to prove it, and when we prove it, it asks for witnesses. We supply 5, 4, and 3, which indeed do form a Pythagorean triplet. 3 squared plus 4 squared equals 5 squared. And we produce a proof, and then we can put this proof into a verifier in Vampire, and it would say that the proof is valid. If we put different triplet, which is not a Pythagorean triplet, then it would say that the proof is not valid. This is available on GitHub. You can download it from Anoma GitHub. Try it, run it. We would be happy to hear any feedback. A second component is Taiga. Taiga is something like an operating system for distributed applications that enables private, we call them shielded, state transitions. It is UTXO based. It relies on validity predicates, which are declarative smart contracts, and it can make atomic state transitions of arbitrary complexity. And to operate, the only thing that Taiga needs as an operating system for this application, it only needs a data storage to run on top of. So, being UTXO based, Taiga stores its state in the form of nodes, which are immutable structures with multiple fields. We would take a look at 3 of them, which are value, how many or how much of something is there. Governing app, which is what kind of node this is. Is it USDC, Ether, Bitcoin? And ownership app. Nodes are not stored on chain, they are stored off chain. You can store your own nodes. Finally, we can store our crypto on a thumb drive. And on chain, we only store data to validate a node to make sure that it's legit and it was not yet spent. Every transaction, as it is in UTXO, and nodes come in, and then the same amount of nodes come out. Okay, just a second. One of the slides got mixed up to a different place. Here it is. Validity predicates in Taiga are declarative smart contracts that Taiga uses for programming the apps. They do not describe how to get the result. They describe what this result should look like. They describe intents. It's a very different programming paradigm because, well, it's declarative and not imperative. And as a mental exercise, we can try to think what an ERC20, for example, would look like in declarative form, because there is no balances. We're in UTXO now. There is no reentrancy or things like that to think about. We just define what is allowed as a state transition. So, for example, owner of a node can burn it and produce a new node of the same value with a different owner. This is equivalent to token transfer, and so on. You can just list all the allowed state transitions, and basically you're done. Validity predicates are, of course, arithmetic circuits so that we can produce zero-knowledge proofs. And today we're using Halo 2 for that, and we rely heavily on Vampire to do that. So how does Taiga works in general? How do we do these intents? And how these intents are expressed, and how do they turn into transactions? Let's say we have Alice and Bob, as usual, and Alice has a note of 1 Bitcoin in her name, and Bob has a note of 10 Ether in his name. And this is our existing state. This is where we are right now. But it happens that both Alice and Bob want to change their state. Alice wants to exchange her Bitcoin for Ether, and Bob wants the opposite, and they're both okay with the 1:10 exchange ratio. So here is what Alice wants. Alice wants to have 10 Ether node in her name. This doesn't exist yet. This is just what she wants. And Bob wants this. He wants a node of 1 Bitcoin in his name. Alice is okay to burn, to destroy her name, her node, if she can get this. She cannot just give this to Bob because nodes are immutable, so she cannot change the owner there. She needs to destroy this. And Bob is okay to destroy his node if he can get here. So here is the desired state, and both Alice and Bob are okay to destroy the existing state if they can get a desired state. And this is it. These are intents. This is Alice's intent. She wants to destroy this to get this. This is Bob's intent. He wants to destroy this to get this. Intents destroy existing nodes or existing state and create desired nodes or desired state. But this is not yet committed to blockchain. These nodes don't exist yet. They only exist in the form of intent. And these intents are floating in the intent mempool. So now solvers, they would look at the mempool and they would see these two intents, and they would see that these two intents are indeed compatible. Meaning that they produce a balanced transaction. 1 Bitcoin is destroyed, 1 Bitcoin is created, 10 Ether is destroyed, 10 Ether is created, nothing is lost, nothing is minted out of thin air, so we are balanced. This means that this would be a valid transaction. So they will create, a solver would create a transaction out of this 2 intents and submit it to the data storage. As I mentioned before, Taiga can run on any data storage, and in the case of Anoma, it runs on Typhon. So what is Typhon? Typhon is an engine for ordering and concurrent serializable execution of transactions. What do these words mean? As we mentioned before, blockchain is a database of state. And what do we typically want from a database? We want to have high availability. We have that. We want to have high integrity. We definitely have that. And we want to have high throughput. Unfortunately, we don't have that usually because most consensus algorithms, in particular Ethereum consensus algorithm, Tendermint, for example, they use serialized execution. So to overcome this, instead of serialized execution, we should do serializable execution. So what's the difference between serialized and serializable execution? Serialized execution is non-concurrent. It is by definition 1 by 1. And this means that there is a practical upper bound on performance of any network that uses serialized execution. Whatever is the performance of one CPU core, however fast we can do transactions single-threadedly, this is how fast we can go as a whole network. Serializable execution is concurrent, but there is a condition on this concurrency that the result of concurrent execution must be equivalent to some serialized execution. How can we achieve serializable execution of transactions on blockchain? Well, we can try to compute unrelated transactions concurrently because this is safe. If transactions are unrelated, we don't have to worry about concurrency. So to determine that transactions are unrelated, this means that they have to work on clearly separated parts of state. In Typhon, state is stored in the form of key value store. So transactions declare key subspaces that they read and write. And it's easy and fast to determine non-overlapping key subspaces and group transactions for concurrent execution. There's a lot more I could tell you about, but we're limited in time. So this is an overview of Anoma architecture. User indicates their preferences through a wallet using user interface. The wallet transforms these preferences into intents in the form of validity predicates and intents, and they are sent to the solvers. Solvers combine those into transactions, and then the rest of this is very typical for, they're similar to other blockchains. So the biggest differences are located in this area. Unfortunately, that's the time we have. I would be happy to answer any questions. I hope I sparked your interest in this project. Follow me on Twitter, check us out at anoma.net or on our GitHub. There's lots of different very cool projects that we're working on. Thank you.
Any questions? Here.
Thanks for the talk. Is there an equivalent of MEV in this system? Like, are those intents openly visible to everyone in the pool, or are they encrypted?
MEV, right? That's a good question. So I'm personally not an expert on MEV. I know that a lot of conventional MEV that we see, for example, on Ethereum or in other chains, some of it is no longer a problem in this architecture. There is still some area, some possibilities for MEV, and I know that a lot of my colleagues, they work on this issue and they do research in this. But me personally, I'm very, very far away from that, unfortunately. I can maybe contact you with somebody who is doing this in the team.
Thank you for the insightful talk. Vampire specifically seemed very interesting. So would love to learn more about, in the slide that you talked about vampire, it showed that we can compile from, say, Socrates or Circom to vampire, then we can actually prove that in Halo 2 or, yeah, Plonkup, things like that. Is that actually possible today? Like if I am a Circom developer, can I actually prove circuits in Halo 2 through vampire?
Some of these paths are possible today, but not all. So Alucard and Juvix are two languages that are developed in Helix. So these are developed by us. This compilation is under heavy development right now. This does work. From here, you can go to Halo 2 and Plonkup right now. There is definitely work happening on supporting other languages, but I don't know the current exact state of this, how far along the team is. So right now, for example, what I do, I write straight in Vampire, and then I go here. So it's a shortened path. But yeah, there is a lot of development happening there, and I'm sure one of the languages, one of these two is the support is being worked on. It's at some stage of readiness, but I'm not sure exactly what stage of readiness it is.
Okay, any other question?
Thank you very much for the talk. So these intents, are they essentially zero knowledge proofs, and are they written in Vamp IR? Or I don't, yeah.
Right. Okay, so intents. We have intents in the form of, so this is a simplified schema of how this works. Apart from what we indicate as nodes and how these nodes should, what nodes should be destroyed and what nodes should be created, everything is also, in addition to that, we also have validity predicates that are written as arithmetic circuits. So every node has a validity predicate, and then we also have a validity predicate, the user's supplied validity predicate for their intent. And altogether, every individual validity predicate must be proved to be correct. And then all of this together is sent to a different circuit, which is like a Taiga circuit, that verifies that all the proofs were valid and produces a proof of verifying the proofs. And then this final proof, this is what gets submitted to the chain. So that's how it works.
Okay, so there are two rounds of proof generation. There's validity proofs constructed for each of the for each of those for each intent, and then the whole transaction gets wrapped up in another proof.
Yes.
As well. Okay, I see. Okay, cool. And then on the Vampire question, so there's this project OpenZL that I think was created by Manta that it seems like it does a similar thing. I'm just wondering if you're aware of that project and if you can talk about some of the differences between OpenZL and Vampire. If you're not aware of it, that's okay too. But
I'm not familiar with OpenZL, but I will look it up.
Okay, cool.
Thank you. Yeah. OpenZL, right?
That's right, yeah.
Okay, one last question.
Great talk. So I was wondering, how do you verify different states from the different depth? Because each depth maybe has its own proof generation. So how do you make a verifier work just across different depth?
You mean here? So how do different apps have different states?
Different depth has different states. Since the proof is since the depth has its own proof, so how do you make the proof can work across different depth?
Okay, so the apps are, all the apps in Taiga are validity predicates, and all the apps are stored in nodes, and the nodes themselves are the state. So the nodes have a reference to an app that governs them, to a circuit that governs a particular type of node. So this Ethereum node and this Ethereum node, they're different nodes, but they have reference to the change to the state that happens for Ethereum app. Somewhere else, there might be a different transaction that changes a different part of the state, but in this transaction, we don't care about that. And they all have the same proof system. They all work on, they all produce Hello 2 proofs, and this happens at the time of execution of transactions.
Okay.
I hope I answered your question.
Okay, that once again, thanks Vasily for the great talk.
Thank you.
So we will have like 30 minutes break. The next talk will start at 4 p.m.